Hello everyone, I'm Ali Neshati from the Department of Computer Science, University of Manitoba, and I'll be presenting our paper BezelGlide, which is an interaction technique with graphs and smartwatches with minimal screen occlusion. Smartwatches are being used to collect the data and provide information to the users. We know that this information will be presented to the users by various visualization techniques, as you can see some of the examples here. Adding interaction to these visualization techniques is really important as a tool to help the users get more insights from the visualizations. And this is something that previous researchers addressed as a concern, which is about need for more in situ interaction with visualizations, specifically on the smartwatches. Because of the small form factor of smartwatches, interacting with these wearables is challenging. This is because direct interaction with the small screen of smartwatches by the user's finger will block the content on the smartwatch display, which is known as the screen occlusion problem. To solve this problem, the smartwatch bezel is one of the ways proposed by many researchers in HCI. However, these proposed techniques are designed for specific purposes such as text entry, and most of these techniques require additional hardware in many cases. As you can see here, in these images, although using the smartwatch bezel minimizes the direct interaction with the smartwatch display, it doesn't really and completely fix the screen occlusion problem. So in our first experiment, we investigated how interacting with different segments of a smartwatch bezel can occlude the content from the user's point of view. So in the first experiment, we asked participants to hit targets on the smartwatch bezel, and we used a mounted camera and a helmet to capture images from the user's perspective to measure the screen occlusion. And as you can see here, this is a pretty interesting result that we got from the first experiment. Interacting with the segments on the top left corner has the worst screen visibility, and interacting with the segments on the bottom and also on the right side of the screen have the screen visibility of over 90%. And this heat map is one of the contributions of this paper, which is really important and interesting to us. So based on the result of the previous experiment, we designed our partial BezelGlide technique, in which the users only interact with the part of the bezel that has more than 90% screen visibility. So whenever the user touches this part of the bezel, there will be a line connecting user's touch point with the other part of the bezel, or the projection area. As the users move their fingers to the right or to the left side of the interaction area, this line will move to the right or to the left side of the display accordingly. The intersection of this line and the data points on the chart will show the value of the data point to the user. To compare the performance of our BezelGlide technique, we designed a full BezelGlide technique which uses the entire bezel to interact with the chart. We also compared our technique with the Shift technique, which is a pretty well-known technique to overcome the screen occlusion issue, specifically on small displays. We also investigated the role of walking and standing mobility conditions, which are two of the most common mobility conditions smartwatch users interact with their smartwatches. This part is really important because previous researchers addressed the lack of in situ interaction with visualization techniques, which is one of the most common things people use their smartwatches. This is the main result of comparing these three techniques. As you can see here, partial BezelGlide performance was significantly faster compared to the other two techniques, because basically we minimized the screen occlusion issue, which is basically the second contribution of this paper. Also, many of the participants in our experiment, they addressed this in their comments, and they liked how the screen occlusion was minimized in partial BezelGlide, which was really interesting to us in this paper. These are further details and findings in the paper that I highly recommend you to read the full paper to get more insights from our paper. We tested our technique with line graphs, but we also showed that how partial BezelGlide technique can be generalized to other types of graphs that are common in smartwatches. For example, as you can see here, we demonstrated how partial BezelGlide can be used to interact with bar, pie, donut, and radial bar graphs, which are common graph types on smartwatches.